Hello everyone, I am Abdullah Khan from Prairie University, and today I am excited to share our work on automated pore detection in FDM 3D printing using deep learning. And this work has been accepted at WACV 2026. So let me start with the problem. In FDM 3D printing, porosity is a critical defect that weakens the layers and reduces the mechanical strength of printed parts. Right now, most monitoring methods are indirect, things like thermal imaging and acoustic sensors, and they require additional hardware. But more importantly, there is no approach that can actually show you where the pores are at the pixel level, and there is no public dataset for this problem. So what we did is pretty straightforward. We mounted an endoscope camera right next to the print head, as you can see in figure 1, and it captures the printing process in real time. Then we use deep learning to automatically find and segment those pores. So our first major contribution is creating the first annotated dataset for this problem. We printed using chicken feather fiber reinforced PVS composite and recorded about 17 minutes of video. Then we extracted frames and carefully selected 1607 of them for annotations. And this was all done manually. We drew polygon masks around each pore to get at the exact boundaries. So figure 2 shows that what this looks like. The raw printing footage is on the left, and on the right you can see all those pores outlined with our annotations. Now, why is this actually hard? Well, if you look at figure 3, the histogram tells the story. The pores are really small and the median is only 277 pixels, and more than half of them are under 300 pixels. They also have these irregular shapes and they don't stand out much against the material. So we are trying to find tiny weirdly shaped things that barely show up in the images. That's why traditional methods don't work well here and why we need these advanced models. So we tested 4 different segmentation models to see what works best. YOLO V8 and YOLO V11 are the newer, faster models designed for real-time use. On the other hand, Mascar CNN and DeepLab V3 are more established methods that give us good baselines. So we made sure everything was fair, same dataset split, same training setup, and we ran everything 3 times to make sure the results were consistent. So alright, so here are the results in table 2. YOLO V11 gets the best accuracy at 92.9%, but here is what really interesting. YOLO V8 is almost as good at 92.6% and it runs at 60 frames per second. So that's real time, and the model is only 23 megabytes, so you could actually deploy this in a factory. The other models struggled more, like Max RCNN got 90% accuracy, but look at the precision and recall, only 61.5%. That means it missing a lot of ports. And if you look at figure 4 here, this plot shows the trade-off between speed and accuracy. And YOLO V8 is right in that sweet spot where you get both high accuracy and real-time speed. So now let me show you what it actually looks like in figure 5. So we picked 3 different cases on purpose. The top row has lots of pores packed together and the middle row has just a few scattered ones, and the bottom row is blurry. So the kind of thing you would actually see during printing. So if you look across, YOLO V8 and YOLO V11 do really well in all 3 situations, and the boundaries are sharp and accurate. On the other hand, Mascar CNN is rougher and misses details, and DeepLab V3 Plus tends to blur pores together, especially in that crowded top row. So the YOLO models are definitely more reliable. Now let me show you this working in real time. So what you are watching here is YOLO V8 processing actual printing video at 60 frames per second. And as the pores from during printing, the model is detecting them instantly and drawing those blue bounding boxes and segmentation masks around them. And you can see the confidence scores showing up as well. And notice how it's catching everything, the large pores, the tiny ones, and the masks are following those irregular shapes really accurately. So this shows that automated quality control for 3D printing is not just about theoretical anymore, it is actually ready for real world deployment. To wrap it up, we built the first dataset for pore segmentation with over 1600 annotated frames. We tested 4 models and found that YOLO V11 gets the highest accuracy, but YOLO V8 is the winner for actual deployment because it's fast and accurate as well. So going forward in future, we want to expand this to other defects like cracks and test it on more materials and connect it to the closed loop systems that can actually fix problems in real time. And the dataset will be public on the GitHub link shown here. And thank you so much everyone for watching.